Cool. So yeah, I'm Illia, co-founder of Near Protocol, and I'm here with Sreeram, co-founder of Eigenlayer. Do you want to give a quick intro about yourself and Eigenlayer?
Yeah, absolutely. Hi, everybody. Thank you so much for staying for this talk. I'm Sreeram. I started the Eigenlayer project 2.5 years back. Was an academic at the University of Washington, Seattle, where I ran the UW Blockchain Research Lab, working on consensus, scaling all of this stuff. Eigenlayer, and the word Eigen, German for your own layer. Anybody can build whatever they want on top of it. That's our vision. And particularly what we do is we allow the decentralized trust underlying Ethereum. You know, people stake money and then make a promise that they're running the Ethereum protocol correctly. And what we allow people to do is to make additional promises that they run other protocols correctly. So instead of Ethereum being this like fixed stack, it starts becoming more, permissionless for people to build arbitrary new distributed systems on top. So that's what Eigenlayer does.
Awesome. So we just announced a partnership last week.
Yay.
So for those who are not familiar with Near started as a layer 1 protocol focused on sharding and scalability and user experience. And then over time, we're kind of evolving in what we call blockchain operating system, really trying to offer kind of a set of tools to developers to build applications in Web3 open web space. And as we see, there's a lot of challenges with kind of running layer 2 applications and layer 2 rollups. And so the kind of idea that came in as we were starting to offer data availability for rollups is to also provide a fast finality to create a fast interaction between rollups. So why do you think this is important? What kind of use cases this opens up? Why got you excited?
Yeah. Firstly, super excited to be part of this partnership. I remember back in 2018, Illia and Near offered to build Ethereum 2.0. And I'm really glad we're making it happen today, one way or the other, If you look at the roll-up era of Ethereum, I think it's a doubling down of this vision of permissionless innovation. If you go back to Ethereum to pre-Ethereum, right? Whenever you want to launch a new chain, you have to go start your own, infrastructure, mining or whatever at that time. We had a bunch of coins, pre-Ethereum. But what Ethereum did is to say, hey, here's a common infrastructure, but anybody can come and build permissionlessly new applications on top. And with the emergence of the roll-up era, what happened is they said, no, it's not just applications that can be built on top. You can start building new chains, called rollups on top by offloading the computation. So instead of running all the computation on this massive decentralized network, you offload the computation and submit a proof that the computation was done correctly. And so this was intended as a mechanism to scale Ethereum massively. And what we've seen is this amazing evolution of new kinds of proof technologies, many zero-knowledge provers, interactive fraud provers, all of these things show up in the Ethereum landscape. I think we can attribute all of that to the permissionless nature of people being able to build rollups. One way of thinking about it is permissionless sharding, right? So it's shards, but anybody can create these shards and build it. But there is a bunch of fundamental problems in that landscape. And one of the fundamental problem is all of these guys who are offloading the computation still need a place to publish the inputs or outputs of these computations, right? Let's say I offload the computation and do the computation myself and then make a claim that this is the outputs of this computation. Other people need to be able to read it and see that I'm doing the thing correctly. If they want to challenge me or if they want to continue my computation beyond my existence. And so that requires a data availability layer, a place to publish the data. Okay, that's problem number one. So the nature of rollups, if you want the optimal Ethereum security, you have to write all the data to Ethereum itself. And the throughput of Ethereum as a data layer limits what set of rollups can be built on top. So that's problem number one. Then there are other problems in the rollup era, and one of the problems is the time to finality. If you're a rollup, one of the things that you can offer is instant finality by running a single central sequencer. The sequencer says, pinky promise, I'll not do anything bad, right? This works when there are a couple of big rollups because, you can trust these guys. These are major companies. They're not going to screw you. But when there are thousands of applications running as rollups, you simply don't have the trust bandwidth for so many people to be making such soft promises. So you need, you can get Ethereum layer trust if you wait for these rollups to settle their computations onto Ethereum. But that takes a long time. There's a lot of latency in actually computing these proofs, aggregating these proofs, putting them on. You want to get batching gains, so you don't want to do it frequently. And then Ethereum itself takes 12 minutes to finalize a block. So add all of this up, you're up in like hours to actually finalize, sometimes days, to settle back to Ethereum. So you want to have a fast layer which can assert that this is the state of the rollup even before Ethereum can make assertions. And this is the concept we are calling a finality layer. A fast finality layer, a layer where like you can do you can get high economic security assertions that this is the state of this rollup and it won't be reverted. Or if it does get reverted, I know so much of ETH or NEAR is going to get slashed. So that's the concept of a fast finality layer. The thing with the fast finality layer is it starts accruing a lot of interesting properties because now it becomes a layer of composability across these different rollups because a place which can give a certain amount of economic assurance that this is how settlement's going to happen basically means you can start interoperating across these different rollups. So you can do fast bridging. Illia was particularly telling me about the asynchronous state model, which is inherent in the NEAR protocol. Maybe you can comment.
Yeah, so there's an interesting question that you asked me was like, why is NEAR doing all this, right? Because, NEAR...
Actually, Illia and I were in a workshop in Hong Kong sometime back, and, he was on the side. The debate was between monolithic L1s and modular L2s, and Illia took the side of like integrated or monolithic L1s and won the debate. And now he's sitting here trying to say that NEAR is helping Ethereum become modular. So I'm trying to understand what's going on here.
Yeah, and so the original idea, right, when we started NEAR was kind of the realization that if you want to scale, you do need to have parallel computation. That's not, I don't think that's like a amazing insight. But as soon as you start doing parallel computation, at some level, you will need to ensure that you have an asynchronous environment where every, be that chain or a smart contract, is running parallel to others kind of on different machines. And so NEAR was designed with that in mind, kind of from the bottom up, with the idea that every single account, every single smart contract on NEAR is its own chain, like logically speaking. And so because of this, we've optimized two things. One is how to create still composability in this environment, in highly asynchronous environment. And then the other side is how do we make a user experience and developer experience such that they don't need to know about it, right? So if you go right now to a NEAR's block explorer, you actually don't see shards. You don't see that there is like a sharded network with lots of kind of parallel computation, because as a developer and user, you don't actually need to know that. And so that's driving factors for us. Like how do we kind of hide the complexity and offer developers a easy to use tooling? And so this resurgence of layer 2s is really just, as you said, is just a form of sharding. Is a form of like, oh, actually I can run my own, be that like smart contract or environment in parallel to everything else. And they face exactly the same problems that we, when we started designing this, is like, well, actually we want to settle them fast across each other. We want to ensure that you have like one transaction that can hit multiple layer 2s. you want to make sure that as a user, you don't need to like switch, 500 networks. Who has more networks in their MetaMask than fits on the screen, right? So those are all the types of experiences that Near been from the start designed to kind of really deliver, right? And kind of to do that, Near was designed to be a very scalable data availability layer. Like on the consensus layer, we actually provide data availability for our Near, account chains. But we can offer that to anybody else external as well. We are able to run actually a full EVM as a smart contract on Near as well. So you can actually have like a real-time finality on the transactions like for EVM. So Aurora is an example of that. And so expanding this, right, expanding the kind of this asynchronous composability that we're building to layer 2s kind of is very natural from perspective of, if developers want to build in this way, we should support it and we should offer the benefits we already have to these developers. And then at the same time, we continue abstracting out the experience, right? We continue making sure that the front ends are unified, that you don't need to actually like ideally even switch networks when you're interacting with them. And there's like more and more tooling coming on that side. But that's kind of the idea is like, it's not that, it's modular versus monolithic. Near is actually like modular inside. It's just, the goal is to remove that complexity from developers and users. And ideally, you should be able to now choose you want to run your own kind of sequencer server or choose a shared sequencer, which is Near. And you have data availability, and you can get the fast finality. And like from perspective of developers, they should be able to send transactions that hit multiple of these things and kind of they discoverable between each other. And the interesting thing about, because Near is asynchronous, actually every single smart contract on Near is designed to be multi-chain. So if you like the Near swap contract, actually the way it works, it receives a message that tokens were deposited. And it sends a message to say, transfer tokens to somebody else. It doesn't actually matter where that message came from the smart contract on Near itself, on another layer 2, or even on Bitcoin. And so we're actually working on like opening that up even more from a developer perspective. So you can build those like highly multi-chain asynchronous applications that actually can route information and liquidity between. But for that, you need fast finality of all these chains. And you need a way to guarantee that actually the state and these messages incoming and outgoing are actually routed. And this is where our partnership with Eigenlayer comes in to actually get these guarantees and get Ethereum security on this.
Yeah, that's super exciting. Maybe we can talk some numbers on what kinds of performance we can expect in this system. On the finality time, like what's the finality time that we are looking at?
So Near block is 1.2 seconds. And so you should be able to pretty much have like a communication within 3 seconds.
Wow.
So data published, Eigenlayer, validators run it, multi-sign on it, and then publish it back. And so with that, you already can have next layer 2 or another Near contract to pick up the messages.
That's super cool. And in terms of data throughput?
So Near right now is about 4 megabytes per second on a shard. And so we have 4 shards. So 16 megabytes per second, or like 1.2 seconds. And this is with the plan in Q1 to actually increase number of shards.
Yes.
And so that's a pretty sizable, like this is,
a lot of data.
I think more than dunk sharding is planning.
No, definitely more than dunk sharding.
And so, yeah, that's pretty sizable. So bring all your layer 2s to Near.
Awesome.
Yeah, and it's 8,000 times cheaper, just, while on that. So I think the interesting question like that for the audience here is, given this is coming online, let's say Q1, what kind of interesting apps now you can do, right? Because if you have this kind of faster composability, now ideally you should be able to unite liquidity better. Mm-hmm. You should be able to unite kind of user accounts, user information better. So we can just brainstorm here. We haven't prepared that much, but some interesting applications for this kind of layer.
Yeah, so one of the things that the vision is with these multiple thousands of rollups kind of a world is we talked about some of the other problems about finality and so on, but shared liquidity is a major problem, right? Each rollup has its own fragmented liquidity, then it's going to be very difficult for these rollups to compose. It's theoretically possible to store all the liquidity on Ethereum and then pull from it as needed, but that is also limited by the finality time, right? And the bridging time back and forth to Ethereum. So what I expect to happen is, in a layer like this, where there is super fast finality, and lots of rollups can plug into a shared source of liquidity. The liquidity will start accumulating in layers where you can access it very easily. So you can start seeing many applications, many swap protocols or whatever, but they use a shared liquidity residing in the finality layer, and then people pull it on demand, some kind of just-in-time liquidity provisioned across rollup. So we can start imagining new kinds of protocols that will come in that will allocate this liquidity to these different layers.
Yeah, I think one interesting kind of considerations is as you modify the rules around DA, what you can do, you can actually have more kind of asynchronous kind of composability, where let's say if you borrow some amount of money, you send it to multiple layer 2s, and they cannot settle their DA until they return the money in the next block, right? And so you can have this kind of more custom rules that now allow to have a more kind of composable experiences. This is like a flash loan, but in this more asynchronous environment. And so you can have, I think it's per use case. I don't think it's like a generic way, but you can have, multi-chain atomic swaps. You can have, if you have forced inclusion and force on, X condition to settle the layer 2s further, you can actually have this interesting models of kind of uniting the applications in between chains, or uniting accounts in between chains, or have I need to pay something there, but my tokens are on this layer 2. You can actually have that being executed for you by either operators themselves or some liquidity provider, like some kind of operator on the other side. And so I think those will be interesting use cases, and I think that's where it will be interesting to offer more programmability around DA settlement, where instead of just validating pure, rules are followed, there's additional potentially set of conditions that are required to settle. And so operators need to kind of ensure these conditions are met.
Oh, that's super interesting. So it's a more intelligent DA layer rather than purely just dump your data. But that's a different model from what most people are building.
Yeah, but I think that's a way to start ensuring more composability, because that's how you get kind of this post conditions and preconditions executed. So maybe switching gears, right? I think Eigen started this kind of restaking movement, but right now there's a lot of kind of projects popping up around this. What do you think about kind of multi-chain restaking landscape? Is Eigenlayer planning to be more multi-chain? Wink, wink.
We're right now focused on Ethereum, and our roadmap is to start enabling a whole bunch of new services that can be built. So we are much more focused on what are the sets of new services rather than expanding to chains. Inside Ethereum itself, I think one of the things we are looking at is expanding beyond just ETH staking. There are lots of assets in the Ethereum ecosystem, like all the rollups that might be building on Near, for example, may have their own native tokens. Those tokens can then get staked on a common platform. One of our reasons for focusing on one chain is, when you have assets across multiple chains, and when you want to write a new kind of a service, now this service needs to be written in such a way that you can write slashing and other things across multiple chains. So this makes it more complex for writing these adjudication protocols. But if you're adjudicating on one chain, so in our vision, Ethereum becomes the adjudication layer, trust and adjudication layer. You supply the ETH, and then that ETH goes into all these protocols. But supplying may not only come from ETH, may come from all kinds of tokens, which either are natively present on the Ethereum ecosystem or can be bridged securely into the Ethereum ecosystem. All of those can participate in the Eigenlayer restaking protocol. So that's our vision. We're also building this interface for what we call, I built a service that is rooted in Ethereum security, but that service will be accessible throughout the cryptoverse. Like, I want to access this AI inference protocol or some other thing that is built on top of Eigenlayer, but that can be accessed anywhere because it's bridged, and there's a native service that can then take it everywhere. So that's the vision that we're building towards.
Yeah, it makes sense to focus and kind of get the product going. I guess like the interesting other side of this that I think like people use layer 1 and layer 2 very kind of freely without either fully understanding or just like it kind of being lazy to describe things. And so I think that one question that might be, so like, at least like from my perspective, I see in the future between all of these pieces, right, we'll see a lot more kind of unification of security. And I mean, you guys are actually kind of doing that as well, where you're offering anyone, like, let's say if Near wants to get more security, actually the partnership we have will also validate Near's blockchain on Ethereum validators. And so to actually rewrite history of Near, like now, like you will need to like reconfirm it with Eigenlayer, and which will not be confirmed, right? And so if somebody wants to get additional security, they can double check with AVS and see like what is the actual history signed by Ethereum validators. And so the question I'm kind of continue pondering is between that and ZK, I think the security itself, like security budgets itself, will go down because like you actually can borrow security from other places, and you can unify security in general of all the chains using these methods, right? Like with ZK, you can just say, hey, I have a proof now that this was executed correctly, and DA is published, and now everybody can ensure that without needing to recompute, right, and kind of pay pretty hefty fee for running of hundreds of validators for all the chains. So I'm curious how you think about it, and then also like would love to kind of introduce some ideas.
Yeah, I mean, you use this term chain abstraction, right? Like, from the viewpoint of the users, really, does it really matter that, it's X chain versus Y chain? And my answer to this is right now it does, and eventually it should not. And why does it matter right now? Because different chains have different security properties. And the abstraction of security is a precondition for abstracting chains, right? When I'm transacting, I need to have an assurance on what is the guarantee that my transaction went through, what is the guarantee that my transaction cannot be reversed, what is the guarantee that my application will continue to execute new transactions. All these different properties together is what makes the security guarantee of a chain or a particular user. And if we can abstract all these properties to say that, hey, I go and transact on any chain, it almost doesn't matter what the chain is, because when I transact, I get an economic assurance that if my transaction gets reverted, transaction should not get reverted, but if my transaction does get reverted, I have an insurance of X ETH or like X Near, and my transaction is less than that, so I can be assured. So in order to create chain abstraction, we need to create security abstraction. In order to create security abstraction, I need to give very tight cryptoeconomic guarantees through the chain, and there needs to be mechanisms to pass this information across the different layers. I agree with Illia that like the concept of layer 1 or layer 2 is not clear what we are actually referring to here. In a world where security becomes much more fractal in nature, like you can share security across different ecosystems much more fluidly. So in this world, I think abstracting the ability of a user to not have to worry about like where they're getting it from is definitely super interesting. There's also an aspect of what is the composability landscape that I'm operating in, because I want to run an application. I don't really care about what chain it is on, but I do care about what I can interoperate with securely. So that becomes the new way in which we can talk about this.
Yeah, I think indeed, like layer 2 was kind of this idea that you don't need to think about the security because it's borrowed from layer 1, and there is some way to compose, although usually it's just meant the interface work, the MetaMask works. But I think going forward was the idea that you can borrow security, or you can use zero-knowledge proofs, which just compress, in a way, the execution. Now you have the ability to kind of say that all of the chains that kind of within this framework, I call it cross-settle on each other, right? Like Ethereum can have a type 1 proof, which is a full zero-knowledge proof from Genesis till now that says like this is a state as of right now under the consensus. And then for Near, you can, we're working with a Polygon on ZK Wasm prover, which will allow to have the same proof for Near. And so you can put the Near proof on Ethereum. You can put Ethereum proof on Near, right? And as you do this kind of cross communication now, you kind of cross-reference in security. And then you can start doing that with other chains. And so you'll need to now to revert anything, or at least, or to change the kind of rules of the engagement, you need to kind of upgrade everyone at the same time.
Yeah, so that is the complexity with that kind of a system, is to hard fork one chain or to upgrade one chain. Now you have to upgrade all the chains.
So Near actually was designed with like voting on consensus layer for upgrades, and so we can actually vote on like new, for example, circuit as well there. And I think Ethereum is trying to figure out how to add an opcode for EVM as well.
Yeah.
Because I think like the reality is everybody wants to have a way to validate ZK proof of their own state machine inside the chain itself and for others. And so I think like we will get there. Obviously it will take some time for that all to mature.
There is also the issue of like, a chain is designed natively to be secure against even 51% of your own validators being malicious. For example, if that happens and then the data is withheld, then the idea is that you can fork the chain. So when you build like systems that cross-settle, there is this pressure that when you fork the chain, then all the chains have to be forked. So there's a bunch of issues to resolve there to get what I call unconditionally interoperable systems. But getting ZK proofs gets us a long way there, because it gets you the validity conditions being cross-referenced and checked across all these different systems.
Yeah, but I think, this is where Eigenlayer can pretty much lend a hand to get like a first order confirmations before ZK proofs are like produced and like kind of communicated and settled everywhere. And then, so we kind of will have almost like different levels of latency to guarantees, like same as, what we're working on, right? Like we have within, 3 seconds, we have X amount of dollars guarantee that this is a final state. But then you still settle on Ethereum, which gives you even bigger guarantees. And and ZK proofs are produced and settled on Ethereum, right? So you have like this kind of different latency, guarantee, composability requirements, and within that also like a fork choice, kind of forkfulness in that space within those specific. But I think like for practical use cases, right? Probably few billions of dollars of security is enough to for the most use cases. And so I think this is where, practically speaking, the security unification will happen sooner than like full theoretic completeness. And what it means, yeah, indeed, like as a user, you'll now be able to use all this without like thinking that thoughtfully, like, oh, I don't trust this chain because it's run by like potentially one computer, because like, oh, actually, but it settles on the same framework, it has the same ZK proof. So I think that is, like, we're getting there really quickly. And at the same time, with cheap DA, with like fast finality, you're also getting like really good parameters on composability. So I'm really excited kind of to see all this starting to play out in like pretty much Q1.
Yeah.
I guess like to finish with something to daydream on AI Web3. I guess we learned right before that we were working with the same project.
Yeah.
So I think that there's an interesting kind of philosophical point that you don't want decentralized companies running your AI inference, right? Maybe model training, whatever, like if the model is published and inspectable, but you don't want mission critical inference to be run by a centralized company, because there can be a sitting engineer there who's like, oh, if this API key, then insert this into the prompt, or even like modify the model. And if Goldman Sachs is asking, then sell all the stock output. And so you want the guarantees around the output. And there is only a few ways to do that. One is with ZK, but it's not scaling yet to the level. One is through multi-party computation. That is 5 minutes per token right now, so very slow. And finally, there is by running a bunch of validator nodes which have GPUs who can actually do inference and co-sign on it. And this is where Eigenlayer is an interesting opportunity to kind of bootstrap that.
Yeah, so one of the things we're seeing on Eigenlayer as an exciting direction is the idea of co-processors or like stateless lambdas. So imagine you're sitting on Ethereum and you're running Uniswap, and instead of the Uniswap liquidity pool being like provisioned statically, you want the prices to be, price ranges and ticks to be updated dynamically. One of the ways you can do it is to say that you commit to an AI algorithm, a protocol by which these things get updated based on the past prices, trades across, multiple dexes or whatever inside the blockchain. But to do this, you need a trusted input. Somebody needs to run the AI and give you the output in a trusted manner. Because if this output is compromised, you may say that instead of 1 ETH is $2,000 something, say 1 ETH is $20 and then just raid that pool. So it's a very, very risky thing to actually outsource. But using Eigenlayer, if you get a certain promise that you have this much amount of economic security, and you make sure that you don't allow trades more than that value within the challenge period, then essentially you can get a very, very tight cryptoeconomic system where you get these inputs are trusted because they're underwritten with a certain amount of capital, and if as soon as that capital promises that input, you just go ahead and run that system. And later, if it turns out to be wrong, you can slash these guys and redistribute it back to the harm parties. So it's a very exciting vision for intelligent DeFi, right? Because DeFi is right now based on very fixed, simple mathematical equations, but really anything in the real world has to be highly adaptive to the circumstances and the conditions, and AI is a natural way of bringing it in. So that's a possible direction that I'm excited about.
Yeah, and I think within this framework, you can also have the model to be hidden, so it's not actually visible to everyone. Because the other part was current DeFi, because the formula is known, like that's not how market makers work, right? Like if all market makers had like published their models, then they would not be like that actually.
To get privacy, though, I think we need the ZKML type things to work, or some kind of fully homomorphic encryption. Because in the model I'm talking about, where like you just outsource to some validators to run the model has to be at least reasonably public.
You can probably like shard the model where like everyone is like decrypting only their part, and then homomorphic encryption on the output is like pretty cheap. So that's part of the signature.
That's an interesting idea. So we are seeing some threshold FHE type systems being built.
Yeah. All right. Well, I will leave you on this interesting note. If there's like few ideas here to build, given the stack that's emerging. But yeah, thank you, and have a good day.
Thank you so much.